Welcome to the second lecture in abstract algebra. The topics that we'll explore in this lecture include relations on sets, important properties of the integers, and some elementary number theory. Okay, so we'll start with relations. A relation between two sets, A and B, is a subset R of the product, the Cartesian product of A and B. And so a relation contains ordered pairs. Now, a relation on a given set A is a subset R of the Cartesian product of the set with itself. So oftentimes, rather than showing the relation as an ordered pair, that is A, B, for instance, is in the relation, we indicate this with a relational notation, that is, A is related to B. So there are several properties that a relation on a set can have, and so we're going to look at those each in turn. So let R be a relation on a set A. Then the relation is said to be reflexive if for every element in the set the ordered pair AA is in that set, or rather in the relation. In other words, each element A is related to itself. A relation is said to be irreflexive if for every element A in the set A, the ordered pair AA is not in the relation. That is, the point A, or the element A, is not related to itself. A relation is said to be symmetric if for every two elements in the set if the ordered pair AB is in a relation, then this implies that the pair BA is in the relation. So in a symmetric relation, if A is related to B, then this implies that B is related to A. All right. A given relation is said to be antisymmetric if for every two elements AB in the set A, if it is true that both the ordered pair AB is in the relation and the ordered pair BA is in the relation, then this implies that A is equal to B. So again, in relational notation, we have if A is related to B and B is related to A, then this implies that A is equal to B. Now notice that the antisymmetric property is not the true opposite of the symmetric property. So we'll look at what is the true opposite of the symmetric property, and that's called asymmetry, or the asymmetric property. And a given relation is asymmetric if it is true that for every two elements AB in the set A, that if the ordered pair AB is in the relation, then this implies that the ordered pair BA is not in the relation. So again, using relational notation, if A is related to B, then this implies that B is not related to A. Now notice that a relation that is asymmetric satisfies the condition for antisymmetry vacuously. That is, there are no, it will never be true that both the ordered pair AB and BA are in the relation when that relation is asymmetric. And so the hypothesis of the antisymmetry property is never true. And so vacuously, a relation that is asymmetric is antisymmetric. All right? And the final property we'll look at is the transitive property. A given relation is transitive if it is true that for every three elements, A, B, and C in the set, if the ordered pair AB is in the relation and the ordered pair BC is in the relation, then the ordered pair AC is in the relation. So again, using relational notation, if A is related to B and B is related to A, oh, correction, B is related to C, this implies that A is related to C. All right? So now a new definition. Let R be a relation on a set A if for every distinct pair of elements, actually before we do that, if two elements A and B are in the set A and either the ordered pair AB is in the relation or the ordered pair BA is in the relation, then the elements A and B are called comparable. And if neither of these ordered pairs are in the relation, then otherwise the elements A and B are called incomparable. All right? So now a new definition. Again, let R be a relation on a set A if for every distinct pair of elements, that is A not equal to B, in the set, if each pair of distinct elements are comparable, are comparable, then the relation R is said to be, or is called, a total ordering on the given set A. Now, notice that we are requiring that the elements be distinct. And if it is true that every distinct pair of elements are comparable, then the relation is called a total ordering. So notice in particular that it is possible for the ordering, or for the relation, to be irreflexive and yet still be a total ordering. All right? So again, let R be a relation on a set A. If some, but not necessarily all, or not necessarily every pair, every distinct pair, of elements in the set A are comparable, then the relation R is called a partial ordering. On the set A. So notice that every partial order is, every total ordering is a partial ordering. Because by definition of a partial order, it is required that some, but not necessarily every distinct pair of elements in A be comparable. So as every distinct pair of elements in a total ordering are comparable, every total ordering is a partial ordering. But the converse is not true. Yeah, not every partial ordering is a total ordering. All right? So now new definition. Let R be a total ordering on a set A such that the relation R is reflexive, antisymmetric, and transitive. Then the set A, together with this relation R, is called a partially ordered set, or often it is abbreviated as a poset. Okay? Actually, a correction to this definition. Let R be a partial ordering on the set A. Then if that relation is reflexive, antisymmetric, and transitive, then the collection of the set A together with this relation is called a partially ordered set or a poset. So let the collection A together with a relation R be a poset if that relation R is a total ordering, then this collection is called a totally ordered set, or sometimes a linearly ordered set. And yet another word that you used is a chain. So a totally ordered set, linearly ordered set, or chain are all the same, refer to the same object, and that is a order structure on a given set. That is a set A together with a relation that is a total ordering and for which that relation is reflexive, antisymmetric, and transitive, then that collection is called a totally ordered set, a linearly ordered set, or a chain. All right, so we'll look at an example. The set of integers together with the relation less than or equal to is a totally ordered set. And we'll demonstrate that it is. First of all, we need to demonstrate that the relation less than or equal to is a total ordering on the set of integers. So notice that for every two integers, a and b, it is true that either a is less than or equal to b, or b is less than or equal to a. And I'll actually state this, a not equal to b. So for every distinct pair of integers, either a is less than or equal to b, or b is less than or equal to a. One of those will be true for any two distinct pair of integers. And so the order, or rather the relation less than or equal to, is a total order on the set of integers. So now we need to show that this structure is a poset. So we need to show that the relation is reflexive, antisymmetric, and transitive. So first we'll show it's reflexive. It is true that for every element a in the set of integers, a is less than or equal to itself. Because the relation less than or equal to allows for equality and a is equal to itself, this relation holds. That is, every element in the set of integers is related to itself by the relation less than or equal. Okay, so again, it is reflexive. So now we need to show that less than or equal to as a relation is antisymmetric. So let a and b be two elements in the set of integers, and suppose that it is true that both a is less than or equal to b and b is less than or equal to a. Then we can combine this into one statement. A is less than or equal to b, which is less than or equal to a. And so the element b is trapped between the element a on both sides. And so this does indeed imply that a is equal to b. And so as a and b are arbitrary elements in the set of integers, this holds for all every pair of elements in the set of integers. And so the relation less than or equal to is antisymmetric. So next we need to show that the relation is transitive. So let the elements a, b, and c be integers. And suppose that it is true that a is less than or equal to b and b is less than or equal to c. Once again, we can combine this into one statement. We have a less than or equal to b, which is less than or equal to c. And so we can, from this chain, see that a is less than or equal to c. And again, we chose these elements arbitrarily from the set of integers, so it is true for every three elements in the set of integers, and so the relation less than or equal to is transitive. And so we have demonstrated that the integers together with the relation less than or equal to is a totally ordered set. All right, so now a new definition. Let R be a total ordering on a set A such that the relation R is irreflexive and transitive. Then the relation R is called a simple ordering on the set A. And the set, together with this relation, is called a simply ordered set. Now, some mathematicians refer to a simple ordering as a strict partial ordering. Now, I will not follow that convention because the definition for a simple order is that the relation be irreflexive, whereas the definition for a partial order is that the relation be reflexive. And so, while it is true that some mathematicians, and of course the corresponding literature, will make little distinction between a simple ordering and a partial ordering, I will not follow that convention. But for those who do, there is still a slight distinction made. Again, a simple ordering is referred to as a strict partial ordering. In either case, the property of the relation is that one of the properties is that it be irreflexive for a simple ordering or a strict partial ordering. So let's look at an example here. We will show that the set of integers together with the relation strictly less than is a simply ordered set. Okay, so first we need to show that the relation strictly less than is a total ordering. So first we note that for every element in the set of integers, every distinct pair of elements in the set of integers, that either A is less than B, strictly less than B, or B is strictly less than A. And this is true for every distinct pair of integers, and so the relation strictly less than is a total ordering on the integers. So now we need to show that this relation is irreflexive and transitive. So first, that it's irreflexive. For every element A in the set of integers, it is true that the element A is not strictly less than itself. And so the relation strictly less than is irreflexive. So now let the elements A, B, and C be integers, and suppose that A is less than B and B is less than C. Then we have A is less than B, which is less than C, and this does indeed imply that A is less than C, and so the relation is transitive. And so the order structure on the integers consisting of the relation strictly less than is a simply ordered set.